Okay, so the next one is exercise 15, and in this one we have to prove that any proper subgroup of this alternating group A5 has order at most 12. That means every such subgroup must have order that does not exceed 12, and we have to use the result of the previous exercise. So let us recall what this one was. Here we proved that the only normal subgroups of A5 are the trivial group and A5 itself. So let us now see the solution. So we are going to suppose the the exact opposite to what is being claimed here, namely that we are going to suppose that there is in fact a subgroup in A5 whose order is strictly greater than 12, and then we will derive a contradiction somehow. Suppose, and well, not just any subgroup but a proper subgroup, of course. Suppose A5 has a proper subgroup H such that the order of H is greater than 12, then the index of H in A5, of course, if you want you can explicitly mention that by writing I suffix A5, but we understand that things are happening in A5, so we don't write this. Then the index of H is the order of A5 divided by the order of H. Now because this is greater than 12, this quotient will be less than the order of A5, which is 60, divided by 12, that is 5, i.e. the index of H belongs to this set 2, 3, 4. Okay, so the index is less than 5, so it can be either 2 or 3 or 4, but why not 1? That's because if the index of H in A5 is 1, then H has to be equal to A5, but then it cannot be a proper subgroup. That is why. Now because of these values, the order of A5, that is 60, does not divide the index of H factorial, because you see what the factorials are. 2 factorial is 2, 3 factorial is 6, and 4 factorial is 24. They are all less than 60, so how can 60 divide them? H must contain a non-trivial normal subgroup of A5, and this is by lemma 291. If we recall what this lemma says, in general, it's just this. Say you have a finite group G in which there is a proper subgroup H. H is a subgroup of G, but it's not equal to G, such that the order of G does not divide the factorial of the index of H. Then there exists a non-trivial normal subgroup of G that is contained in H. N. This N is contained inside H. So here also H must contain a non-trivial normal subgroup of A5. Non-trivial means not equal to the trivial group. But that is not possible. Why? Because by the previous exercise, A5 has only two normal subgroups. One of them is the trivial group and the other is A5 itself. Now if our H contains such a normal subgroup, then that cannot be equal to A5 because H itself is a proper subgroup. At the same time, it's non-trivial, so it's neither A5 nor the trivial group E. So it's a contradiction to the result of this exercise. But this contradicts the result of exercise 40. So our supposition is wrong. That means any proper subgroup of A5 must have its order less than or equal to 12. It has to happen, which you can write. I am, however, ending the solution here itself. Let's see the next one. 16. Here we have to find all the normal subgroups of S4. All the normal subgroups of S4. The way this solution will start, it will seem like we are just arbitrarily doing something, but it will all make sense eventually. But let me, before I start writing the solution, let me just use some ink. Now the first thing here we are going to show is that although we have to find all the normal subgroups of S4, but our first statement is about the alternating group A4. We first want to show that A4 does not have any subgroup of order 6. Let us show this by contradiction. So we start like this. Suppose A4 has a subgroup H of order 6. Say there is one such subgroup. Now there are two possibilities, either H is abelian or it's non-abelian. Let's see what happens if we assume that H is abelian. Let H be abelian. Then by Stilla's theorem, for abelian groups, H has subgroups, say K1 and K2 satisfying these conditions, that the order of K1 is 2 and the order of K2 is 3. What is it that we have done here? You see, H is an abelian group of order 6 and 2 and 3 are primes dividing 6. So by Stilla's theorem for abelian groups, H will have subgroups of order 2 and 3. What does the general Stilla theorem for abelian groups says? It says that, say you have a finite abelian group G whose order is divisible by some prime P. Then G has a subgroup whose order is the largest power of P that divides the order of G. In this case, we have these two primes and the largest power of 2, for example, that divides the order of H is 2 itself. So there is a subgroup of order 2, just like that there is a subgroup of order 3. Now being subgroups of an abelian group, both K1 and K2 are normal in H. Since these are normal in H must be cyclic, and this fact comes from an exercise that we have already proved by exercise 9 of the previous section. What this exercise says is this: say we are in a finite group G whose order is of this form PQ, where P and Q are distinct primes. We don't, in the original exercise, it's not necessary that G has to be abelian. No such thing is there in the hypothesis. Just the order of G looks like this, where P and Q are distinct primes. And say G has subgroups, some subgroups, one subgroup K of order P, another subgroup say H of order Q, and K and H are normal in G, and P and Q are distinct primes, then G must be cyclic. That's what we have used here. 2 and 3 are distinct primes, and K1 and K2 are normal in H, so H must be cyclic. So now H is a cyclic group of order 6. So it should have a generator of order 6, but because H originally is a subgroup of A4, so that generator of order 6, at least one generator should be there, which is an element of order 6. It should come from A4, but that is a problem because in A4 there is no element of order 6. But this contradicts the fact that A4 has no element of order 6. So that means H cannot be abelian. Now this conclusion may be a little confusing, because you see, our first supposition is that such an H exists. Then on top of that, this is another supposition that H is abelian. So now that we have run into a contradiction, what should we conclude from that? We cannot immediately conclude from this that H does not exist. Why? Because we have just seen that these two suppositions together give us a contradiction. So we cannot just simply from this conclude that H does not exist, because we have to also see that case where, say, H is a subgroup of order 6 but H is non-abelian. Unless we see that case and see what happens there, we cannot rule out the possibility that such an H may exist. Okay, so now it is non-abelian. Now H is a non-abelian group of order 6, so H is isomorphic to S3 by, this is also one of the exercises, and it is exercise 11 of section of the 7th section. H is isomorphic to S3. Now the elements of order 2 in S3 are the 3 2 cycles. We already know what they are: 1 2, 1 3 and 2 3. And what are the elements of order 2 in A4? We keep in mind these elements do not belong to A4 because they are all odd permutations. In A4 we have the identity element, and then we have products of 2 2 cycles, and we also have 3 cycles because they are also even permutations. However, 4 cycles do not belong to A4. And also keep one more thing in mind, that because we are after all in S4, so we have only 4 symbols. So when we are taking products of disjoint 2 cycles, we can only consider 2 of them at a time, because once we consider all the 4 symbols, for example 1, 2 times 3, 4, we run out of symbols. So we write like this, and the ones, that means the elements of order 2 in A4 are these. Now, because these are in fact the only elements in A4 that are of order 2 and H is isomorphic to S3, so all these elements must belong to H. We must thus have being isomorphic groups, S3 should behave exactly like H, or rather I should say H should behave exactly like S3. They are the same thing, but since we do not really know about what H actually is, so I am saying it like that. Anyway, now the point is that S3 has 3 elements of order 2, H also has 3 elements of order 2, fine. But there is a problem. The problem is that these elements of order 2 in H are mutually commuting. They commute with one another. However, the ones in S3, these are not mutually commuting. But these elements in H commute with one another, whereas the ones in S3 don't. So how can H and S3 be isomorphic? This is a contradiction and this contradiction finally tells us that okay, we have in fact run out of options and now we must conclude that H cannot exist. This is a contradiction and shows that there is no such H. That is, A4 has no subgroup of order 6. Fine, so we have shown what we wanted to show. Let us now see what we do next. Now let K be a subgroup of S4 of order 12. Our aim is to show that K is equal to the alternating group A4. That means we want to now show that A4 is the only subgroup of S4 of order 12. We now consider the product of K and A4. Because A4 is already a normal subgroup of S4, the product KA4 will be a subgroup of S4 by a previous exercise, which I am not going to mention. Then KA4 is a subgroup of S4 and we have order of KA4, we know how to calculate this order. This is the order of K times the order of A4 divided by the order of their intersection. And both of them, the individual subgroups, both of them have order 12. So this becomes 12 times 12 divided by the order of the intersection, and this divides the order of the group S4, that is 24, by Lagrange's theorem, of course. Keep in mind, this divisibility comes from the fact that KA4 is a subgroup of S4. Okay, so now after manipulating this relation, what does this imply? You see, we have 24 on this side. On this side we have 24 times 6. So 6 should divide this order. Now since this intersection is a subgroup of A4, we also have the order of this intersection dividing the order of A4, which is 12. So this divisibility relation and this one tells us that this integer is either 6 or 4, but it cannot be 6. Why? Because of this, whatever we proved in the previous paragraph. Due to the previous paragraph, we thus have this equal to 12. But this is a subgroup of A4. So it's a subset of A4, and yet it has the same number of elements as A4. So it must be equal to A4. Since, should we again mention that because it's obvious. Thus, or rather I should write, this implies that the intersection is A4, which in turn implies that A4 is contained in K. But again, A4 and K both have 12 elements. So this containment along with that fact implies that they must be equal. At this time we can mention, since order of A4 is equal to 12, which is equal to the order of K. So now K and A4 are the same thing, same set. So that's what we wanted to show in this second paragraph. Hence, A4 is the only subgroup of S4 whose order is 12. Fine, we still do not see why we are doing these things, but it will now become clear in this third paragraph. In this third paragraph, again we are going to start by supposing something, and then we will prove that our supposition is wrong, from which this time we will conclude something that is related to this, finding out the normal subgroups of S4. Now our supposition is this. Next, suppose S4 has a normal subgroup N which is different from the trivial group, the alternating group A4, the entire group S4, and also has order different from 4. Okay, so suppose there is such a normal subgroup N satisfying these conditions. Now I am going to write some things which I will explain afterwards. Let me first write down. If N has a 2 cycle, then it has all the 2 cycles by the discussion on page 88. This thing I will have to write I think twice more. So let me put a star here. So the next time I have to write this, I will just simply write by star all the 2 cycles, and hence N must be equal to S4 by our lemma, which tells us that any permutation. Okay, let me just first write the things down and then I will explain. By lemma 210(2), this is one thing, which of course cannot happen. Also, if N has a 3 cycle, then it has all the 3 cycles again by star, and hence in this case A4 should be contained in N, and in this case, oh, I forgot to write why A4 is contained in N. What is the justification for that? This comes from exercise 12. In this case, n is equal to A4 or n is equal to S4. Okay, what are we doing here? We understand what we have supposed. We have supposed that S4 has a normal subgroup N, which is different from these three subgroups, and also additionally N has order different from 4. Now this part, after that, this part we have to now understand. If N has a single 2 cycle, then it must have all the 2 cycles. By the discussion on page 88, what does this mean? To understand this, we go back to a discussion that we in fact already had about this discussion. This is something that we are only going to see in the next section, but we have used it already, and this time also we are using it. Say you have a group G. In that group, any group G, not necessarily finite, you consider any 2 elements A and B. You can define a binary relation, and its definition is like this. A is related to B if B is equal to C inverse AC for some element C in G. Okay, and this relation has a name. It's called conjugacy. And 2 elements related by this relation are called conjugates of each other or conjugates to each other. And it turns out that this is an equivalence relation. So it will partition the group into disjoint equivalence classes. We already know these things about any equivalence relation. Now this particular relation of conjugacy and those equivalence classes in this case are called conjugate classes or conjugacy classes. Now these conjugate classes are especially nice to describe for the symmetric groups, like we have S4 here. And that description is this. For the sake of specificity, let us consider S4 because that's what we have here. So in S4 also the conjugacy relation will partition S4 into disjoint conjugate classes. Okay. Now what will there be in these conjugate classes? That will depend on the cycle structures of the permutations or of the elements of S4. For example, say we consider this element. It's a product of 2 disjoint 2 cycles. So its cycle structure is 2, 2. Now the result that we have, we are going to see in the next section. It shows that all the elements of this cycle structure, that means all products of 2 disjoint 2 cycles, form one conjugate class. And for that matter, for example, if we just simply consider ordinary 2 cycles, their cycle structure is this. They will form another conjugate class or conjugacy class. And that is why any 2 cycles are conjugates to each other. Similarly, any two elements of this type having this cycle structure are conjugates with each other. But no element here is conjugate to an element here. We understand these things about equivalence classes. Or for that matter, all the three cycles in S4 form one conjugate class. All the four cycles then again form one conjugate class. So what is it that we are saying here? If N has a two cycle, that means that this is the conjugate class for the cycle structure 2. So it has precisely all the two cycles. If there is one two cycle in N, then you say this A is a two cycle that is coming from N. Then all the other two cycles would also be there in N. Why? That is because you consider any other two cycle B, because they have to be conjugates. So B will be equal to C inverse SC for some permutation C in S4. But now you also recall that N is a normal subgroup of S4. So N is normal, A is in N, so C inverse SC must belong to N for any element C in S4. So that is why all the two cycles must belong to N. That's what we have written here. Okay. So we understood what we have done here. Now if all the two cycles are in N, then N must be equal to S4 itself. Why? That's because we know that any permutation is a product of two cycles. That's what this lemma says. In other words, the two cycles, all of them generate the entire symmetric group S4. So in this case, N has to be equal to S4. Now we understand what is going to happen if, say, N has a 3 cycle. Then similarly, say this is the conjugate class for cycle structure 3. Then similarly, using the normality of N in this case must contain all the 3 cycles. But we already have seen in exercise 12 that the 3 cycles generate the alternating group. So A4 must be contained in N. Now A4 is a group of order 12 and S4 is a group of order 24. N is trapped in between them. So there are two possibilities for N. Either N is equal to A4 or N is equal to S4. And why exactly is that so? That's because due to this containment, the order of A4, which is 12, it should divide the order of N. Also, N is contained in S4, so the order of N should divide 24. So there are only two such possibilities for the order of N. Either it's equal to 12 or it's equal to 24, resulting in these two things. Okay. So now we understand what we have done. But you can see that none of these conclusions that we have here is possible. Why? Because our N is different from E, A4 and S4. So we continue. Since none of the above is possible, N has neither a 2 cycle nor a 3 cycle. Okay. Now based on this fact and the previous paragraph, we are now next going to write something else. Hence, the order of N is one of these. But how? Ideally, I should write other things in between, but that I am just going to say verbally. Let's see how. Now forget for a moment the restrictions put on N. You just consider the fact that N is a subgroup of S4. And S4 has order 24. So we are just going to take the help of Lagrange's theorem first. So the order of N should be a divisor of 24. Now these are the positive divisors of 24. 1, 24, 2, 12, 3, 8, 4, 6, and that's all. Now, okay, now you think of the restrictions on N. First of all, N is not equal to the trivial groups. The order of N, and in fact, we are trying to see what possible values can order of N have. So N is different from the trivial groups, so this is ruled out. N is different from A4, or let us first see, N is different from S4, so 24 is ruled out. N is different from A4 according to our choice of N. So this 12 is also ruled out. But why? That's because in the second paragraph we have proved that A4 is the only subgroup of S4 of order 12. That's why N being different from A4 cannot have order 12. That is why 12 is ruled out. And because of the extra hypothesis on N, 4 is also ruled out because N cannot have order 4. We have chosen N like that. So that leaves us with 2, 3, 6 and 8. Now what about 3? We are saying that these are the possible orders. What goes wrong if we take this? Because 3 is prime, N must be cyclic if this is the case. But then N must have an element of order 3. Now the only elements in S4 of order 3 are the 3 cycles. But N does not have any 3 cycle. So that is why this is also not a possibility, and this leaves us with 2, 6 and 8. Okay. Which means what? Which means N is even. Right? N is even. Now you recall that we have seen one exercise way back when we started group theory. It says that if we have a finite group G whose order is even, then there exists an element A in G which is non-identity element and its square is equal to the identity element. In other words, in terms of orders of elements, there exists an element in G of order 2. Now N is also a group of even orders, so there should be an element of order 2. And the exercise that says that this is the case is exercise 11. Of section 2.3, N has an element of order 2. But now what type of elements of order 2 can there be in N? What type of elements do we have in S4, by the way? We have identity element which has order 1. We have 2 cycles which are of order 2, but N cannot have any 2 cycle. So 2 cycles are also ruled out. 3 cycles are there in S4, which of course have order 3, and 4 cycles have order 4, so they are also ruled out. But we are left with only this type of elements, products of 2 disjoint 2 cycles. Why 2 disjoint 2 cycles? That's because we have only 4 symbols whose permutations we are considering in S4. So once we use 4 of them, we have run out of symbols. For example, you can consider this element. Okay, so they have order 2, this type of elements have order 2, and only they can now, given all the restrictions, they can now be in N. So that's why we write N has an element which is the product of 2 disjoint 2 cycles. But again, because of that discussion on page 88, N will then have all such elements having that cycle structure, which is the product of 2 disjoint 2 cycles, and hence by star all such elements are in N. Now what are those elements? There are 3 such elements. They belong to N. Okay, but now the extra hypothesis that the order of N is not equal to 4, that will now come into play. Note that besides these 3 elements, N being a group must also have the identity permutation. So we are having 4 elements in N already. Since this is not equal to 4, N must contain at least one 4 cycle. But why 4 cycle though? Because let's again see what the type of elements we have in S for E: 2 cycles, 3 cycles, 4 cycles, and elements of this form, products of disjoint 2 cycles, 2 disjoint 2 cycles. E is already there in N, and this type of things we have already considered. N cannot contain any 2 cycle, N cannot contain any 3 cycles, so that leaves us only with the 4 cycles. If one of them is there in N, then N must also contain the others, again by star. And hence all the 4 cycles, of which there are 4 minus 1 factorial equal to 6. How many 4 cycles are there in S4? 6 of them are there. But why though? I mean, if we think of 4 cycles, say this is a 4 cycle, will it not be 4 factorial? Actually, that's not true. You see, if we are just simply thinking of arranging 4 distinct objects linearly like this, then it's 4 factorial. But when we are using these to form cycles which actually are permutations or functions, then that count is wrong. For example, you look at this arrangement and you look at this arrangement. If you ignore the fact that these are cycles and hence permutations and think of only the arrangements of the symbols, they are different permutations. Here the first place is 1, here the first one is occupied by 2, but as functions they are equal. Why? Because this one maps 1 to 2, 2 to 3, 3 to 4 and 4 to 1. This one also maps 1 to 2, 2 to 3, 3 to 4 and 4 to 1. They are the same function. So to count their number, you have to fix one of them and then find the number of ways of arranging the others. That is the number of cyclic permutations. That is why 6. So now besides these 4 elements, 1, 2, 3 and the identity, we have additional 6 elements at least in N. That means at least there are 10 elements in N. So the order of N is greater than or equal to 10, which contradicts this. That means our supposition is wrong. Whatever we supposed about N, such an N does not exist. But what is the consequence of that? Namely, you see, what is it that we have shown? An N which is normal in Sn, that is different from the trivial group, the alternating group A4 and S4, and also that does not have order 4, cannot exist. A consequence of this is that if you find a normal subgroup N of S4 that is different from those 3 groups, E, A4 and S4, then its order must be equal to 4. This is what we are now going to conclude. And now you can, now you realize why this has drastically reduced our search for normal subgroups of S4. The trivial group A4 and S4, these are normal in S4 that we know, but if there is something else, then that something else must have order 4. So, any normal subgroup of S4 different from E, A4 and S4 must have order 4. Now it turns out that S4 actually has a normal subgroup of order 4. One can verify that this subset L consisting of the identity and these elements (1, 3, 2, 4) and 1 4 2 3 is a normal. I think I need ink due to the size of this solution. Without ink we cannot do. This is a normal subgroup of S4. Showing that this is a subgroup of S4 is not very difficult. You just have to show that L is closed under multiplication. Finiteness then implies that L is a subgroup. But showing that it's a normal subgroup of S4, it takes more effort, but I leave this to you. But is it the only normal subgroup of S4 of order 4? Yes, this is the unique one, and that's what now we are going to show. Once we show that, it will be over. Now let say P be a normal subgroup of S4 of order 4. We want to show that P is equal to L. So let us consider PL like what we did with K1 and K2. Then PL is a subgroup of S4, again for which we have used the normality of L or the normality of P. Now the order of PL like before is, this time it's 4 times 4 divided by the order of the intersection, and this should divide again the order of S4 which is 24. Since the order of PL itself is greater than or equal to the order of L which is equal to 4, we must have order of PL Okay, now how exactly are we concluding this from these two things? Note that PL of course contains L, and that is why this order must be at least 4. But you look at the structure of this number, structure of this quotient, it is 16 divided by something, and it should be at least 4. So but at the same time it should also divide 24. So it can be 4 because it has to divide 24, but at the same time you look at the numerator is 16, and this quotient hence must itself be a divisor of 16. In other words, it should be a power of 2. So it can be 4, it can be 8, I mean this whole thing. Anything else? Can it be 16 itself? No, because 16 does not divide 24. So this order must be equal to either 4 or 8. These are the only two possibilities. Since we have already proved above that S4 does not have S4 does not have a normal subgroup of order 8. Have we really? Where? You see, we have in fact shown what so far? We have proved that the normal subgroups of S4 are this. This is normal subgroup, this is normal subgroup trivially. A4 is a normal subgroup, and in fact A4 is the only normal subgroup whose order is 12. In fact, it's just the only subgroup whose order is 12. Anything else, if we have something else that is also a normal subgroup of S4, then it must have order 4. This one has order 1, this one has order 24 of course, this one has order 12, this one, anything else must have order 4. So no place for 8, but normal subgroups. Is PL normal? Yes, it is. Why? Because both P and L are normal. L is already normal, that we just mentioned there itself, and P is normal because we chose P to be normal. Of order 8, and PL is normal in S4, since both P and L are normal in S4. If you want, here itself you can write, then PL is a normal subgroup of S4. You don't then have to mention it here again. So that means the only possibility for PL is that it should have order 4. Since we have already proved these things, P must have order of PL equal to 4. But then PL must be equal to P, but at the same time PL must be also equal to L, and that's how P and L are equal. So let me write like this: P is equal to PL, that is equal to L. But before we end things, let us see why. P is contained in PL just like L is contained in PL, P has 4 elements, PL also has 4 elements, so they must be equal. Similarly, PL should also be equal to L, and so these two things are equal. This. So, the normal subgroups of S4 are these. In the order of increasing order, they are these: E, L, A4 and S4. Now everything is over. So with this, of course, I end the video, and the next update is of course tomorrow. And tomorrow, due to the absence of any upload on the previous Saturday, tomorrow I am going to upload 2 videos, one about groups and one about rings from Gallian's exercises. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.